Okay, there we are. All right, so today's lecture is actually not going to deal with new concepts so much as issues specifically related to homework 2. So if there's one lecture actually that's probably worth rewatching, I don't know if there's any lecture worth rewatching, but this is probably one that has the most, let's say, helpful information for doing homework 2. Okay? So a lot of the stuff we're going to talk about is, I don't know, I entitled this lecture, Overcoming. This is a positive word. It means, you know, you overcome something. And what we're overcoming is our computational difficulty. If nothing else, homework 1 hopefully will have taught you that to even do a simple problem like homework 1, let's call it simple, but really in some ways it is on the grand scheme of a lot of computational problems, but for even that problem there's all these little things you had to do to make it work. This is characteristic of computational science. Okay? For every problem you do, there's usually things you've got to take advantage of and to make the problem work out. One of the problems that scientific computing isn't on a level where you just have this black box, throw in your problem, boom, spits an answer out. Typically, that's not, we're just not at that level that we have software that does this. There are some software codes that do some of this, try to do some of this, but it's not clear that they're going to be running very fast or very efficiently either. Okay, so for every problem you have, you're going to have little issues that you have to deal with, and finding ways to deal with it is really as fundamental as setting up the big structure of the problem. Okay. In particular, I'll say this: one of the things that you really want to take advantage of is anything you know about the problem from an analytic point of view. Okay. So there's one idea, which is have a set of equations. You discretize it up, throw it on the computer. But if you actually know something about the behavior of the system or something mathematically about it that the computer doesn't know, you've got to incorporate that in, because that's often going to be key to making either your code go a lot faster or even making your code work at all. Okay, so the first issue we're going to deal with is, we've already talked about it, but this is one that's easy to keep rehashing. And that is dealing with the stream function equation. And in particular, its non-uniqueness. Okay? So, remember, you're going to have to solve that over and over and over and over again in your code. You're going to just have it in a loop. And we applied some boundary conditions, which were the following. We had periodic boundaries. And the periodic boundary said that when x is equal to negative L, it's the same as being at positive L in x. And when y is at negative L, it's the same as being at y positive L. Now, part of the problem with imposing this kind of boundary condition is the following, and we've talked about this. My general solution to this thing is something like this. If I have a solution, sorry, not to this thing, I find any solution to this, I can add a constant to it. It's still a solution. Why is that? Well, it not only satisfies the equation, because if I take two derivatives in x and y, obviously two derivatives of this constant drop out. You say, well, what about the boundary conditions? Well, they're just periodic. So what's over here, here? If I add c to everything, it doesn't change it. This c still keeps the boundary conditions, still satisfies this. The problem with it is you now have an infinite number of solutions. So again, when you say, let's discretize this, you get into a form ax equal to b, where last lecture we actually created this matrix A. Okay? Well then, you're typically going to do this. Just get for x, it's going to be a backslash b, and your computer will choke. And the reason is, the determinant of that matrix A is 0. When a determinant of a matrix is 0, you can think of it has no inverse. So you can't take this inverse and multiply by b. There's no, when the determinant is 0, there's either no solutions or an infinite number of solutions, and your computer doesn't know how to pick those out. Okay? Now, by the way, I should make this comment. When you do this here, we see this problem right away when we discretize, and you say, well, what about when I Fourier transform? Because we talked about doing this with Fourier transforms, which we'll talk about in a little bit more in a second, which is I Fourier transform an x, Fourier transform an y, and then I just inverse Fourier transform this expression. You know, where do I get a singular matrix? You don't. In fact, the Fourier transform automatically, essentially, picks out for you some constant c. You don't have to go do it. Now, again, for this problem, you say this is a mathematical difficulty that you have to worry about. But is it physically relevant? I mean, if you do this and you're imposing something like this and you have this infinite number, what does that mean about the physics of the problem? Or does it mean anything about it? Well, you remember that this stream function psi was defined in the following way. So that its partial derivative in y with the negative sign gives you the component of velocity in the x direction, which we called u. And its partial derivative with respect to x gives you the velocity component in the y direction. Okay, so in other words, if you have a piece of fluid in here, your u is that way, your v is this way, and the velocity, so you know your total velocity is kind of made up of these two components. So all it cares about, though, is the partials. So, again, this constant c, no effect. So although I have this infinite number of solutions, when I actually go down, I'm only getting one velocity out of it for every point. Okay, that's very important. You'd hate to say, I have an infinite number of stream functions which give me an infinite number of velocity possibilities here. Because then you go, well, how do I tell which one's the right one? And you wouldn't be able to do that. But here, since it's a derivative, the c falls out, boom. You've got it nailed down. Okay, so that's that. The other thing is, too, when you look at the evolution of the vorticity, this is also where the stream function pops up. You say, well, if I have the stream function here, does it care about the constant c? Well, remember what this quantity is. It's equal to d psi dx, d omega dy, minus d psi dy, d omega dx. And again, the only way this appears up here is as a derivative of the stream function, here and here. So again, you ask the question, does the constant c matter? No, it doesn't. So far what we've shown is that this constant c simply doesn't make a difference. I can have it be 10 or 1,000,000 or square root 3 or 0, whatever I want it to be. It will not change the fundamental physics of the problem. Okay? Very important. So even though it's non-unique stream function, there is a unique vorticity, advection, diffusion equations. Okay? All right. So that's an important issue. The other thing you have to, when you do this kind of problem, part of the reason we don't have the uniqueness is because the boundary conditions don't pin this down. What are the boundary conditions could I have? For instance, I could say, let's consider some other boundary conditions. I could have said, well, how about making, for instance, something like this? Not have it be periodic, but having it be pinned. Suppose my stream function is 0 at the edges of my domain. So not periodic, but in some sense this is periodic, but I've also said it's pinned. These are 0 at the domain. Now, if I take a function and add some constant c, I can't just add any c. The c has to be very specific. This now pins c down. So c has to be It's a unique value now. Okay? So in that case, if you'd had these boundary conditions, you wouldn't have to worry about this problem. You remember in the first homework in your part B where you discretized everything and the two boundary conditions you had to handle separately. Well, same thing here. You discretize this whole thing, and on the edges, you'd have to impose this boundary condition, which changes the matrix A. Makes it not singular. Okay? So right now, as it is, the matrix A that we have for studying this problem, right, which is what we did in class last time, this matrix is singular. But now if you go back through and say, well, now let's impose the boundary conditions. Well, the boundary conditions come from here. The boundary conditions say, oh, well, that's 0. It's going to change the way matrix A is written. And in fact, it's going to make it non-singular, so its determinant exists. And you don't have any problems. That's one possible boundary condition. You could also have what are called no-flux boundary conditions. And what those are is where you basically impose the derivative at the boundaries. So something like this. The normal derivative at the boundary is 0. Okay? It's called no-flux boundary conditions. Well, in this case, you say, okay, well, what does that mean? Well, here, you can ask the same question. What kind of solutions am I going to get? Obviously, I have to impose this boundary condition here. But so it's going to be a little bit different matrix. But check this out. I'm posing that boundary conditions. I'm going to get now a different matrix A. But if I have a solution and add C to it, is it still a solution? It is. I'm now taking the derivative of the boundary. C drops out altogether. So C does not get pinned down. So you see that for no-flux boundary conditions or periodic boundary conditions, either one of these, I have to deal with this singular matrix. Okay? Well, how do you deal with it? Part of the point I wanted to, I guess, make here is that you simply don't care whatsoever what this constant C is. I mean, you could care, but it doesn't matter. It doesn't affect the physics whatsoever. Given that, then, it's completely arbitrary what you pick C to be, right? So all I really need to do is make it so that matrix A is not singular. So I can go to the first row, first column, and I talked about this in class last time, and say, do this. The value is supposed to be is -4. By changing it to 0, I've arbitrarily said at the boundary there's some condition that makes this 0. And that's going to pin down a certain constant C. I don't care. Make this 10, 20, -√3. It simply doesn't matter. It just can't be -4. Because if it's -4, the matrix is singular. Okay? It's as arbitrary as that. I could have done something else. I could have gone and said, how about in the first row, the fifth column, there's a 0 there, and let's make it I don't know, √3. Pins down another constant. Who cares? Yeah?
You want to take it far enough to -4 now, because it could be like almost rank deficient with a computer if you take like -3 or something like that.
It turns out if you take like, no, actually, as long as you're, I mean, if you're even like -3, -2,
It works.
-5 works fine. No problem at all. It's when you get down to -3.99, then you have to worry. Because then all of a sudden the determinant's getting really close to 0. And that's the only time you really have to worry. You still get 16 decimal place precision, so if you put -3, the determinant might not be huge, but you don't care. Okay? So, this is a practical issue that doesn't affect the physics, but if you just kind of blindly go through and say, I'm going to discretize this, and again, think about the difficulty you have if you're just trying to make a canned routine to do this for you, right? So someone builds a package and says, I have this package that solves these kind of equations. You say, okay, I'll give you the equation, and I'll give you the boundary conditions. This is what a canned package would probably want. Well, you just gave it something that has a singular behavior of that matrix. Does the computer know then what to deal with that? Is it going to just go ahead and do something on its own? You have to control that piece to it. So this is what makes it a little bit tougher problem. Okay? And this is also why you see that making a canned routine for this stuff is hard, because there are these issues floating around that you have to hold the computer's hand through. It's not like you can just say, do this problem for me, and it does it all, and it says, oh yeah, this problem, it doesn't really matter that it's singular, because I know this is a string function. The computer doesn't have that reasoning ability. Okay? Unless you specify specifically this problem, and this is how I take care of it. Okay? So it's a little bit difficult to just kind of take a problem of this nature and just have a black box run it for you. Okay, so that's one issue got to take care of. All right? Any questions on that? Issue 2, we'll move on next. Issue 2, which again I've mentioned, but we'll go in a little more detail now. And that has to do with the Fourier transform method. We can go back to this problem here and say, okay, I want to solve this. And basically what we derived in class is you say, okay, well this is nothing more than 2 derivatives in x, 2 derivatives in y is equal to omega. And if I Fourier transform in x and in y, what does that give me? Well, if I Fourier transform in x, that's going to pop out a minus kx squared there. And if I Fourier transform in y, remember y and x are independent here, so I could take the derivative, interchange the integration and derivative, so that's why I can do this. Fourier transform in y, then I get, oops, this will be minus ky squared. Okay, and then you solve for the stream function, which is equal to minus omega kx squared plus ky squared. So all you have to do is calculate this quantity, inverse Fourier transform it. And you can use, it's two-dimensional, so you can just use FFT2 and IFFT2. So FFT2 will take the two-dimensional Fourier transform of your vorticity, omega, and inverse Fourier transform 2 will take this thing here and inverse Fourier transform in 2 dimensions to give you back your two-dimensional string function. It's as simple as that. The only problem you've got is that kx and ky, remember how we define kx? We did this in the computer last time. Kx would be something like this, 2 pi over L, and then times, I said it went from 0 up to n over 2 minus 1, and then negative n over 2, all the negative 1. Remember, this is those wave numbers that we had before, shifted, because that's what the Fourier transform does. And ky has something similar. Here's the point. What is kx1? Zero. What's ky1? 0. So when I go to calculate this, there's a point where kx1 and ky1 both appear. They're both 0. And this thing is a divide by 0 problem. Okay? Your code will stop right there. MATLAB will say, I would divide by 0. It's illegal. It is illegal. Okay? So what's the problem? The problem is that I actually do have kx and ky being 0. Okay? So how to fix it? So I need to fix this problem. So you see, one of the things is, on this level, when I Fourier transform back, it doesn't care about the non-uniqueness issues. It goes, Okay, so the determinant's 0. Well, it picks out a constant. But it does care about the divide by 0. In fact, actually, they're kind of related. The divide by 0 here is the manifestation of this thing coming out. Okay? So let's talk about how to do this. Well, one option would be to say, okay, I have this thing. All I have to do is make sure I don't divide by exactly 0. So why don't I put in some small. The EPS command pulls out basically the numerical round off in the computer. This is some number that's like on the order of 10 to minus 15. What it guarantees you is that if I do this calculation, there is never 0 down here. This could be zeros, this could be 0, but I have something non-zero there. So I can divide by it. Well, granted, I'm dividing by a very, very tiny number, but who cares? MATLAB will crunch right through that. Okay? Now, part of the problem with doing it this way, and by the way, I found this is a fairly standard method that when I've asked around and looked around, you just put some small correction in there. You say, well, okay, and then now every term works fine. But you're kind of like every this k of x goes from, has n modes and n modes here, and so this isn't a square, so it's n squared components, and every single one of them you're dirtying up with this, as it were, or adding a little bit of numerical round off with it. And the only one you care about is this one component where k x1 is 0 and ky1 is 0. So why don't you instead, and this is what I recommend highly, this is like my Consumer Reports highly recommended. There's a check mark and a circle. I think that's what it means. You definitely want to do that one. Okay? All you have to do is when you define these things, you do something like this. After you define your vector k of x and k of y, well, kx1 is this 0. We'll make it 10 to the minus 6 or something small. Make ky 10 to the minus 6. So now the only components that are going to be affected is when this is 1, kx is 1, and ky is 1. You take that out altogether now. And you're not adding an error of 10 to the minus 6. Remember, you're squaring this, so this is like 10 to the minus 12 when it's down here. But the point is, now you have something that's 10 to the minus 12, not 0. Okay? So this gives you fairly nice results. And that fixes up your problem. In general, anytime you have to do this, this is kind of the thing you want to do. The other recommendation that comes for this, kx squared and ky squared. Remember, you're in a computational domain like this. K of x really is your x wave numbers in this direction. K of y is your wave numbers in this direction. What I recommend for here is that this is the Fourier transform of the vorticity, right? The vorticity is some stuff in 2 dimensions. And you're going to FFT it using FFT2. So this thing here is in, if this is n components and it's n by n, this thing here is an n by n matrix. Okay? And you're going to take this n by n matrix, FFT it. So this is a matrix like this, and now you're dividing by this. Well, kx and ky, with the way I've defined them, they are vectors. Right? Let's look how I define it. Kx is like this, ky is like this. At this point, kx and ky do not know that they're supposed to be in this direction and this direction. Right? Kx is just a vector, and ky is just a vector. They don't know that they mean x direction and y direction. Only you know that. Okay? So when you go to write this thing, you have to think about, well, how do you make this calculation here? Because partly what you want to do, since you're going to use this over and over again, is not say, well, take this thing, square it, plus take this thing, square it. Why not just calculate this whole thing once and keep that around? Keep the whole quantity kx squared plus ky squared once. Otherwise, you're doing multiplication, 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 addition. 5 operations with these big matrices every single time you do this, versus just having one matrix that does this whole thing. Okay? So in order to take care of this problem of telling which way is which, you use what's called the mesh grid command. And what mesh grid does is says, I have these two, these are capital KX, KY, little kx, little ky. And what mesh grid does is take this vector and that vector, and now put directions to them. Now it knows that kx is like this and ky is like that. And what it produces, these things are vectors, but now kx is a matrix. It calculates kx in this direction, but for all the different levels of the discretization. Right? Because kx is the same whether it's here or here or here or here or here. It's independent of y. And ky also varies this way, but it's independent as it moves across an x. So this now, both kx and ky are matrices. So if you want to calculate the bottom of that thing, now what you could do is take this kx and call that, there you go. That's what that is. Where when you, this kx and ky both have fixed up that 0 component by making kx1 and ky1 10 to the minus 6. And then you just carry this matrix around with you, the big K matrix. Yeah, Pierre.
Omega, the Fourier transform omega is a matrix, right?
Yeah.
What we have in the denominator, k, is a matrix too. Mm-hmm. So what we do, like, is that dividing?
Yeah, okay, so to do the division, all you have to do is say, okay, now I have this thing and this thing here. So this is, so let's call, let's suppose we have omega. The transform omega is going to be something like this. Omega is a big matrix, and if I FFT to it, it'll give me another matrix, which is WT, which is omega transform, let's call it. Okay? So if I want to calculate psi transform, I would just say psi transform is equal to minus omega t dot. The dot tells it to do component by component. And then all you have to do is say, well, my psi is then I FFT2 of psi t. You're done. So you come in, you have this thing as a matrix. The nice thing about this thing here, you can just define it on the outside of your loops, all your loops, because once you define it once, you're fine. Because remember, this is going to be inside of your ODE loop. Because you have to keep, every time you update the stream function, you have to, every time you update the vorticity, you have to update the stream function. Right? So you have to come in, you say, well, I have a new value for the vorticity. Okay, great. Take that new vorticity, transform it, divided by this, inverse Fourier transform it. Now calculate, update my stream function, vorticity again. Okay? Hello, Larissa.
Those small numbers, the 10 to the minus 6,
how
would it change if you put in larger numbers there? Like, how is that changing your
So,
solution? I mean, obviously
I've
you
never
can't
put very
put
large
0,
numbers in
but
it.
I guess I'm just wondering what effect that has.
Essentially, so these modes are supposed to be 0, or very close. So to get close and practical to the problem you have, you want them to be small. I've never taken them above 10 to the minus 3. So frankly, I don't know what will happen. You can try it out.
I guess you're dirtying up your solution in some form. So what direction are you, dirtying it in? I guess is kind of what I'm saying.
So it's a good point, and I don't know exactly what will be the manifestation of this thing is if you start just making it big. So, all right. Any more questions about this? Practical stuff on when you solve this thing with the FFT. Okay, so we've kind of knocked off 2 methods. Notice that all the problems are coming from solving the stream function. Right? Everything's coming from this part, right there. what I'll show you in a minute is that there's not really that many problems with the rest of the thing. It's just a simple, discretize and solve. Here, because we're solving this ax equal b problem that is singular, well, then we have all these problems. But we can get around them all. But this is no different than 99% of the problems you'd have to be doing if you were doing a research problem. Like, that there's that you weren't handed a code, just say, here, just put in some numbers and go. But if you actually had to write a code for something reasonably hard, chances are this is the kind of process you'd have to go through. It's a development thing that you start thinking, oh, yeah, geez, that's a problem, so what do I have to do to fix it? Okay, that's a way to fix it. That's a problem, what do I have to do to fix it? It's the same thing as homework 1, is you keep finding all these little things they have to do. And part of the reason I like the homework so much is because I think they make you do this. This is where they really learn. I mean, this is stuff that you can't learn in the textbook. Right, Pierre? Not even in France can you learn that in a French book.
Probably not.
No, I'm sure. Unless, I don't know, maybe. What do I know? I have to overcome the whole reading French barrier. That would be hard enough for me. So, okay, more questions on this? We'll move to the third part. The third bit of information concerning solving this problem. All right, so consider what we're actually solving now, which is, so we've been talking about solving the string function, but really, in the end, it's going to be coupled to this equation here. Okay? This is your advection term, your diffusion term for how the vorticity gets smeared around in space. Where, again, you have this okay. Now, at least for homework 1, the way we're going to solve this problem is we're going to solve it by discretizing this problem up. Okay? We've talked about, and remember, we have this coupling here, and we've talked about different ways to solve for the string function from here. We can do ax equal to b. We can do FFTs. We can even, when we do ax equal to b, we can use LU decomposition or one of the iterative solution techniques. So there's a lot of different ways to solve that. Fine. But now what about solving here? Here I've just said, okay, let's just discretize it and go. Well, that means we have to calculate this stuff. Now, what do we know happened to this under discretization? It just became basically a matrix A. If we break up this problem to a bunch of points in X, a bunch of points in Y, then the Laplacian with periodic boundary conditions, which we constructed, was just, that just turns into a matrix A. So, what do you have to still do for this part of the homework? Well, notice that in addition to this in the problem, you have this term. And this term here requires you to have x derivatives and y derivatives. So let's go ahead and talk about those for a moment. In particular, let's say, suppose I wanted to calculate the x derivative or vorticity. Well, what do? Let's just do a second order discretization. Something as simple as that. Okay? Now, if you remember, we said, let's let omega m and be omega of x of m, y sub n. Then this formula basically comes out to be partial with respect to x of omega mn is equal to omega m plus 1 n minus omega m minus 1 n all over 2 delta x. So we have this fundamental formula here. So for instance, if we start writing a few first things down, we say, okay, well, this means that d dx of omega 1, 1 is equal to, actually, omega 2, 1 minus omega n 1. Remember, boundary condition. So it's omega 2, 1. This should be omega 0, 1. But remember, so this is basically saying, if I'm at this point right there, that's omega 1, 1, and I want the x derivative, I need to use the two neighboring x points. Well, one of them's right there. Where's the other one? There's none here. But it's periodic boundary condition, which means it's this one over here, right? Because this is the same as this. That's what that gives you. And then you can say, well, what about the next one? Oops. Well, that's omega 2, 2 minus omega n 2, 2 delta x. Remember how we stacked? We went up this way, and then we went 1. Then we started moving up points this way. That's what we did before. And so this point relies on two neighboring points, which is this one here and that one there. This one here relies on this one and that one there. So you can see that you have to construct this in very much the same way we did with the matrix A. Okay? So let me show you what the structure of this thing looks like. Or let me say in bigger terms, d omega dx is going to be equal to 1 over 2 delta x times the matrix B omega. Everybody has a 1 over 2 delta x in it. The matrix B looks like the following. Zeros everywhere here, and then ones, zeros all the way over here. You have negative 1, negative ones. Here, negative 1, negative 1, negative 1. So it looks something like this. There's ones on the diagonal here, which start over n spots. Remember, n points this way, n points this way. And remember, that leads us then to a matrix which is size n by n. That's what the matrix B is. So we have to stack all our vorticity components. So we get ones over here, we get negative ones over here. These negative ones actually continue over here, and the ones that hit down here, there's ones down here. So if you go through this and go through and see how this works, when you take this thing out and write it down as a multiplication like this, this is the structure you get. I should mention, by the way, that the nice thing about the sp.dix command that we did in class on Friday was that that matrix had 9 diagonals. To get this matrix, all you have to do is take out 5 of them and switch signs on some of them. If you look at the structure, buried within that matrix A is this. Your job partly is now to go back and say, okay, so that's what this matrix B is. And the matrix B then does differentiation with respect to x. And what we're going to say is the matrix C does differentiation with respect to y. And you get to calculate what that looks like. Okay? Once you have A, B, and C, you already have A. B's right there. You get to go calculate what C is. Once you have those, the problem's easy at this point. Because with A, B, and C, you go, okay, I want to solve this problem. What do? All right, well, I have Look at it as think of it as a central system of differential equations. I have omega t is equal to nu del squared omega minus psi omega. Let's write this out. Nu del squared omega minus this thing here is psi x, d psi x d omega y plus d psi y d omega x, right? When you discretize this thing, what does this become? This omega now becomes a big vector for all the values of the vorticity as we stack them up. Then this becomes, under discretization, omega t equals nu, what's two derivatives in x and two derivatives in y? That's our matrix A. Minus, I have a derivative with respect to x, and I have a derivative with respect to y. So this becomes 4 delta x delta y. This becomes b vector psi, and this becomes c does that make sense as this term is? So d psi dx is, that's the x derivative, so that's the matrix B. d psi dy, that's the matrix C, and one of them has 1 over 2 delta x, one of them has 1 over 2 delta y. That's it. Plus 1 over 4 delta x delta y, and then here you get c psi, and then b omega. That's it. So in ODE 4.5 or any of these solvers that we've been working with, this is our whole right-hand side, right there. All you need to import is your matrix A, B, and C. And when you're in your right-hand side, the first thing you need to do is calculate what the stream function is, throw it in here. Notice the matrix A here can now be the original matrix A. In other words, you don't have to say that A11 is 0 in this case for this guy. Why? Because this is doing a multiplication of a matrix, not a solve. Okay? So this matrix A can be the singular matrix A. And then B and C, you're going to calculate. It's as simple as that. You just throw that into ODE 4.5 and it just chunks through it. Remember, the purpose of ODE 4.5 or any of the ODE solvers is say, give me a big system of differential equations. First order differential equations. That's exactly what I've got right there. Under discretization, everything becomes this huge system of differential equations. All I need is the right-hand side, and I will solve it for you. All you need is give me initial conditions. You give it an initial vorticity, it'll just start chunking through this thing. Okay? So that's the way you want to set up this code. And like I said, you define A, B, and C outside of the ODE call, but you have to pass them in. And once they're in there, just use them. Any questions on that? All right. So this is just a practical day in the sense of, if you understand these three issues we talked about today, life's going to be much easier in homework 2. But you see already, homework 2 is just this kind of a generic problem, yet it has to have these. You're already seeing that you have to massage everything to work. Okay? Very much like homework 1. Higher level. Because there's a little bit more things that can go wrong in this one.